In my previous videos I've looked at gravitational fields, I've looked at electric fields to the extent that we've looked at what they are, what they affect, field strength, field patterns, and we've looked at uniform fields and contrasted those with gravitational fields which cannot be truly uniform but do approximate to being uniform in certain circumstances. We looked at gravitational potential before, and we defined gravitational potential as the work done against the field in bringing, well, with gravitational fields we talked about 1 kilogram. Here we're going to talk about 1 coulomb, but we have the option of either positive or negative in defining this. Well, I say we have the option was there. So it is defined as the work done against the field being plus 1 coulombs from infinity to the point that is the electric potential at a point in the field. And the expression for that is that V is the symbol for potential as it was with gravitational fields. Q is the charge producing the field. In coulombs, of course. And R is the distance from Q to the point. So you can see that if Q is positive, then the work done against the field in bringing plus 1 coulombs in, so if we draw plus Q here, and we have our test charge here, and we're bringing that in from infinity, clearly we will have to do work against the repulsive force due to the field, and so the potential will be positive. However, if this was negative, the field would do the work, and so the potential will be negative. Now remember, in a gravitational field, the potentials were always negative because the field will always do the work in bringing 1 kilogram in from infinity to this point because gravitational fields are always attractive. So here we have another difference between electric and gravitational fields, and that is that the potential can be positive in an electric field, but it can't be positive in a gravitational field. So let's look a little bit in detail at the field lines, so the potential in the field. So here's our charge, and here are 3 concentric circles around our charge. And let's say our charge is positive. So I'm going to arbitrarily assign plus 300 volts to this line, plus 200 to this line, plus 100 to this line. My point is that my equipotentials around an isolated charge are concentric circles, that is to say circles with the same center, centered on the charge. So this distance out, the potential is plus 300 volts from this positive charge. If I drop 100 volts, I go out to here. You see how this distance, dropping the next 100 volts, is larger than this distance. So for equal changes in potential, the changes in distance get bigger. The changes in radius get bigger. Now, remember, when we drew the field lines around an isolated point charge, they were radii. And these are circles centered on the charge, which means that the radii, the field lines, always cross the potentials at right angles. That's important, A, because it's something that you need to recognize and be able to apply, but what it means is the force is acting at right angles to any motion along the equipotential. Now, if you think back to your circular motion work, and remember I said circular motion applies really quite heavily in the fields work as well. If you are moving at right angles to the line of action of the force, going back to your mechanics, there is no work done. The force is at right angles to the motion, and so there is no work done, which means there is no change in energy, which means something can orbit in this equipotential forever. But there are specific orbits, perhaps. If you think about electrons orbiting the nucleus, there are specific allowed orbits. But your charge can orbit in this equipotential, just like with a gravitational field. Your satellite can orbit at this radius forever, assuming no losses. There is no work done by the gravitational force in a gravitational field. There is no work done by the electric force in an electric field to maintain that orbit. No change in energy, no work done, therefore no need to input energy. So there you have the equipotentials around an arbitrary positive charge. I have assigned values to it, but the point is that this distance, which causes a change of minus 100 volts going from here to here, is larger than this distance, which is nearer to the charge, for the same change in potential. So if I was drawing a third equipotential here, then I should probably have assigned that to be plus 400. So my apologies for that. So plus 400, plus 300, plus 200, plus 100. Here to here is smaller than here to here, which is smaller than here to here. If I was drawing another equipotential, it might be out here somewhere, way beyond the side of my page. But the distance from here to the next equipotential would be larger than this. So there you have the equipotentials around a positive charge. Very similar diagram. Equal changes in potential. R3 bigger than R2, bigger than R1. And again, I should have assigned this to be minus 400 here. Minus 4, minus 3, minus 2, minus 1. Okay. So there you have how we define potential, very similar to how we did in gravitational fields. The equipotentials around positive and negative charges, very similar, but obviously you're always heading towards zero as you go out. So you're getting progressively less negative here, whereas in the previous one, you're getting progressively smaller magnitude. You've got the idea that equipotentials around an isolated point charge, in the same way as around an isolated mass, are concentric circles centered on the charge, and for equal changes in potential, you have progressively increasing distances between those circles. So looking at uniform fields then, you might remember, hopefully you'll remember this diagram, the field lines between two parallel plates. Let's call this 70 volts, let's call this 0 volts, because it is. And if we throw in our equipotentials, remember we said that the equipotentials are always at right angles to the field lines. So in here you're going to have parallel equipotentials. But they have to be at right angles to the field lines out here too, so they're going to curve up so that they cross these lines at right angles and curve down here. So we might have a set of equipotentials that look a bit like this. And I've chosen my values of plus V here, 70 volts, so that I can say I've got 0, 10 volts, 20 volts, 30 volts, 40 volts, 50 volts, 60 volts, and 70 volts. And so in the middle here, I would expect another equipotential, my apologies for that not being absolutely straight, of 35 volts. So equal steps, equal distances. So as you would expect, the potential difference between here and here varies linearly as you go up. 10, 20, 30, 35, 40, 50, 60, 70 volts. So there you have your equipotentials in a uniform electric field. Again, no work done in moving along an equipotential. So let's look graphically then at how potential varies. So I don't want that one just yet. So we said that potential was inversely proportional to the distance from the charge. So you have this 1/r graph. Now, if you compare this graph, I'm saying here, compare this to gravitational potential, you'll remember gravitational potential is always down here. It's always negative. So here you have a graphical demonstration of one of the differences between electric and gravitational fields. So the potential is positive if the charge is positive. It's negative if the charge is negative. Remembering that we're talking about the charge causing the field here, because the test charge is always +1 coulombs. Now, in terms of drawing these graphs, sketching these graphs rather, you need to be able to distinguish between the potential and the field strength. Now, the field strength is a 1/r squared relationship, so it is a much steeper curve. So I'm saying here, compare these graphs to the potential for gravitational fields, because that's down here all the time. Whereas with electric fields, you have a positive one as well if the charge is positive. And also, in terms of sketching them, the field versus distance graph is a 1/r squared graph and has a steeper curve. Note that both the field and the potential curves are asymptotic to both the y and x axes. That is to say, this rises up and it approaches the v-axis but never reaches it. As r tends to 0, v tends to infinity. If you think about it, dividing any number by a very, very, very small number makes a very, very, very big number. And the same thing happens down here. So it is asymptotic, approaches but never touches the v-axis. And equally, as you make r enormous, v falls to a magnitude near 0 but never gets to 0, because no matter how big you make r, something divided by r will never be 0. So it approaches but never touches. These are the things your examiner is going to look for. That steeper 1/r squared graph for the field strength, the asymptotic to both axes, the fact that you know that this graph is a mirror image of this one in the R axis, but that you have negative potentials in both gravitational and electric fields, but you have positive potentials, potentially, if you'll excuse the pun, in electric fields. So you have these graphs then. And just a couple of extra points for you in relation to electric fields. If you're a mathematician, then you'll be probably fairly happy that the work done is the integral between 0 and r of f with respect to r. So that is the area under the force distance curve, of course. But the work done is Q delta V. That's where you'll get that from. And if you integrate f, which of course is a 1/r squared relationship, you will get a 1/r. So that then, of course, the work done per unit charge is the potential. So there's a relationship that is useful to you. You don't need to know where it comes from, but I just thought I would tell you that if you're into maths. And the field strength then, again, if you're happy with the maths, going backwards from this, the field strength is the gradient of the potential distance graph. It's actually minus the gradient of the potential distance graph. So there it is. You have what the potential is defined as. You have the differences between gravitational and electric potential to go along with the other differences with the fields that we've discussed. You have drawing the equipotentials. Remembering an equipotential is a line or a surface joining all the points of the same potential. It's almost given to you by the name. It's a line or a surface joining all points of the same potential. You've got that the equipotentials will always cross the field lines at right angles. So in the case of an isolated point charge, you have your field lines, which are radii of the circle, which you would draw as your equipotential. So the field line is always at right angles to the equipotential. The point of that, one of the points of that, is that no work is done in moving around the equipotential. So your charge can remain in this orbit without needing any input of energy, without losing any energy. You have this relationship for the work done in the field, Q delta V. If there is no change in potential, as I was just saying, then there is no work done. And you have how to calculate the electric field strength from your potential graph. And of course, the force then is the field strength times the charge.